Picture this, a world where the ground beneath your feet is a rusty red, the sky above is a pale pink, and the horizon stretches endlessly into a landscape that feels both alien and eerily familiar. This is Mars, a planet that has captivated humanity for centuries, not just for its proximity to Earth, but for the countless mysteries it holds. What if I told you that despite decades of exploration, Mars still keeps secrets that even the brightest minds on Earth can't fully explain? From strange formations that look like they were carved by an ancient civilization to phenomena that defy our understanding of science, Mars is a treasure trove of enigmas waiting to be unraveled. In this video, we're diving deep into 30 of the most baffling phenomena on Mars, each one a puzzle that challenges what we think we know about the red planet. Why does methane mysteriously appear and vanish in its atmosphere? What carved the massive canyons that dwarf anything on Earth? And could there be hidden lakes of liquid water buried beneath its icy surface? These are just a few of the questions we'll explore. So, if you're ready to embark on a journey to a world that feels like it's straight out of science fiction, keep watching. By the end of this video, you'll not only have a deeper appreciation for Mars mysteries, but also a burning curiosity to learn more about what lies beyond our own planet. Let's uncover the secrets of Mars together. Now, let's turn our attention to one of the most iconic and debated mysteries of Mars, the so-called face on Mars. Back in 1976, NASA Viking 1 orbiter captured an image of a peculiar formation in the Cydonia region that immediately sparked imaginations worldwide. At first glance, it appeared to be a massive humanoid face staring up at the sky, complete with what looked like eyes, a nose, and a mouth. The image was so striking that it led to widespread speculation. Could this be evidence of an ancient alien civilization? The idea of a Martian monument, perhaps even a message left behind by intelligent beings, captured the public's imagination and fueled countless theories. However, as technology advanced, so did our ability to study Mars in greater detail. High-resolution images taken by later missions, like the Mars Global Surveyor in the late 1990s, revealed a very different story. The face turned out to be nothing more than a natural rock formation, shaped by erosion and the play of light and shadow. While this explanation satisfied many scientists, it didn't completely extinguish the fascination surrounding the structure. For some, the idea of a face on Mars remains a tantalizing mystery, a symbol of the unknown that continues to inspire both scientific curiosity and wild speculation. What makes the face on Mars so enduringly intriguing? Perhaps it's the way it taps into our deep-seated desire to find meaning in the cosmos. Even though we now know it's a trick of geology, the image still serves as a reminder of how much we have yet to discover about Mars. It's a phenomenon that bridges the gap between science and imagination, challenging us to question what we see and what we think we know. And as we continue to explore the red planet, who knows what other mysteries, real or imagined, we might uncover. Next, we'll dive into another fascinating Martian enigma, the mysterious blueberries scattered across its surface. Now, shifting our gaze to another intriguing Martian mystery, we encounter the so-called Martian blueberries. These tiny spherical formations were first discovered by NASA's Opportunity rover in 2004, scattered across the surface like nature's own marbles. Officially known as hematite concretions, these small, round objects earned their whimsical nickname due to their bluish-gray hue and their uncanny resemblance to berries. But don't let their playful name fool you. These formations are anything but ordinary. Hematite, the mineral that makes up these blueberries, is an iron oxide compound that often forms in the presence of water. This discovery immediately sparked excitement among scientists, as it suggested that liquid water might have once flowed on Mars. The presence of water, even in the distant past, is a critical clue in understanding whether Mars could have ever supported life. But how did these blueberries form? That's where the debate begins. Some researchers believe they were created through a process called concretion, where minerals precipitate out of water and accumulate around a central nucleus, much like how pearls form in oysters. Others propose that they might have formed through volcanic activity or even meteorite impacts. The truth is, we still don't have a definitive answer, and that's what makes them so fascinating. What's particularly remarkable about these blueberries is their uniformity. They're almost perfectly spherical and roughly the same size, which is unusual for natural formations. This consistency has led some to speculate that they might hold clues about the environmental conditions on Mars billions of years ago. Were they formed in a calm, watery environment, or did they emerge under more turbulent conditions? Each theory offers a different glimpse into Mars' geological past, and each raises new questions about the planet's history. The Martian blueberries aren't just a scientific curiosity, they're a window into the red planet's ancient climate and its potential to harbor life. As we continue to study these enigmatic formations, they remind us that even the smallest discoveries can have profound implications. And with every new piece of the puzzle, we get closer to unraveling the secrets of Mars. Next, we'll explore another seasonal mystery on the red planet, the recurring slope lineae, dark streaks that appear and vanish with the changing Martian seasons. Now, let's turn our attention to a phenomenon that seems almost alive, the recurring slope lineae. These mysterious dark streaks appear on Martian slopes, only to vanish and reappear with the changing seasons. First observed by NASA Mars Reconnaissance Orbiter, these streaks have sparked intense curiosity and debate among scientists. What causes them? Could they be evidence of liquid water flowing on Mars today? The answers to these questions could reshape our understanding of the red planet. The recurring slope lineae, often abbreviated as RSL, are narrow, dark lines that emerge on steep slopes during warmer months and fade away when temperatures drop. They've been spotted in various regions, including the rugged terrain of Valles Marineris and the slopes of Hale Crater. Their seasonal behavior suggests a connection to temperature changes, but the exact mechanism behind their formation remains elusive. One leading theory is that they're caused by briny water, salty liquid that flows just beneath the surface, seeping out and darkening the soil as it evaporates. This idea is tantalizing because liquid water, even if it's salty, could potentially support microbial life. However, confirming the presence of liquid water is no easy task. Mars' thin atmosphere and freezing temperatures make it difficult for water to exist in liquid form for long. Some researchers argue that the streaks could be caused by dry processes, such as dust avalanches or the movement of sand grains. The debate continues, and each new observation adds another layer of complexity to the mystery. For instance, in 2015, NASA announced that hydrated salts had been detected in association with these streaks, providing some of the strongest evidence yet for liquid water. Yet, even this discovery hasn't settled the debate entirely. The implications of these recurring slope lineae are profound. If they are indeed formed by liquid water, they could represent one of the most promising locations to search for signs of microbial life on Mars. Microbial organisms on Earth thrive in extreme environments, and similar life forms might exist in the briny flows of Mars. But even if the streaks are caused by dry processes, they still offer valuable insights into the planet's geology and climate dynamics. As we continue to study these enigmatic features, they remind us that Mars is a world of surprises. The recurring slope lineae are more than just streaks on a slope, they're a tantalizing clue in the search for life beyond Earth. Next, we'll delve into another atmospheric mystery, the puzzling spikes of methane detected in Mars' thin air and what they might mean for the possibility of life on the red planet. Now, let's shift our focus to a phenomenon that has puzzled scientists for years, the mysterious spikes of methane detected in Mars' atmosphere. Methane, a gas often associated with life on Earth, has been found in surprising amounts on the red planet, raising questions about its origins and what it might mean for the possibility of life there. Methane on Mars was first detected in 2003 by the European Space Agency's Mars Express orbiter. Since then, NASA's Curiosity rover has repeatedly measured methane levels in Gale crater, revealing occasional spikes that are far higher than the background levels. These spikes are intriguing because methane is a gas that doesn't last long in the Martian atmosphere. Ultraviolet radiation from the sun breaks it down within a few hundred years, which means any methane detected must have been released relatively recently. But where is it coming from? Scientists have proposed two main possibilities. The first is geological activity. Methane could be produced by chemical reactions between water and certain types of rock deep beneath the surface, or it might be released from ancient reservoirs of methane trapped in ice. The second and more tantalizing possibility is biological activity. On Earth, the vast majority of methane is produced by living organisms from microbes to cows. If life exists or once existed on Mars, it could be producing methane as a byproduct of its metabolism. The challenge lies in determining the source. Is it geology or biology, or perhaps a combination of both? To answer this, scientists are using a variety of tools, from orbiters to rovers, to map methane concentrations and track how they change over time. For example, the European Space Agency's Trace Gas Orbiter has been analyzing the Martian atmosphere in unprecedented detail, searching for clues about where and how methane is being released. Meanwhile, Curiosity continues to monitor methane levels on the ground, providing valuable data about local variations. The stakes are high. If the methane is being produced by living organisms, it would be one of the most significant discoveries in the history of science, proof that life exists beyond Earth. Even if the source turns out to be geological, it would still reveal important details about Mars' interior and its potential to support life in the past or present. Methane is a key biosignature, a chemical marker that could point to the presence of life, and its detection on Mars has made the search for life there more urgent than ever. As we continue to explore this methane mystery, it's clear that Mars still holds many secrets. The next time you hear about a methane spike on the red planet, remember, it could be a clue to one of the greatest discoveries of all time. Up next, we'll explore another enigma, the strange shapes and origins of Mars' two moons, Phobos and Deimos, and why their existence continues to baffle scientists. Now, let's turn our attention to the skies above Mars, where two small, enigmatic moons orbit the red planet, Phobos and Deimos. These moons are unlike anything we see around Earth, and their peculiar shapes and orbits have sparked decades of debate about how they came to be. Phobos and Deimos are small, irregularly shaped bodies, more akin to asteroids than the spherical moons we're familiar with. Phobos, the larger of the two, is only about 27 kilometers across at its widest point, while Deimos is even smaller, measuring just 15 kilometers. Their surfaces are heavily cratered, and they both have a dark, dusty appearance, leading scientists to wonder if they might have originated in the asteroid belt. One leading theory suggests that Phobos and Deimos were once asteroids, captured by Mars' gravity as they drifted through the solar system. This idea is supported by their composition, which resembles that of carbon-rich asteroids found in the outer regions of the asteroid belt. However, capturing two such objects and placing them into stable, nearly circular orbits around Mars would require a very specific set of circumstances, making this scenario somewhat unlikely. Another possibility is that these moons formed from debris left over after a massive impact on Mars. Billions of years ago, a colossal collision between Mars and a large object could have ejected material into orbit, which eventually coalesced to form Phobos and Deimos. This theory is supported by the fact that both moons have orbits that are relatively close to Mars and are nearly circular, which would be consistent with material settling into orbit after such an event. Yet, despite these compelling theories, the origins of Phobos and Deimos remain unresolved. One of the biggest challenges is their unusual composition. While they share some similarities with asteroids, they also have unique characteristics that don't quite fit the asteroid capture model. For example, their densities are lower than expected for typical asteroids, suggesting they might be porous or contain significant amounts of ice. Adding to the mystery is the fact that Phobos is slowly spiraling inward toward Mars, and in about 50 million years, it could either crash into the planet or break apart, forming a ring around it. Deimos, on the other hand, is gradually moving away. These contrasting orbital behaviors hint at complex gravitational interactions that could provide clues about their origins, but they also complicate the picture. To solve this puzzle, scientists are eager to study these moons up close. Missions like the Japanese Space Agency's Martian Moons Exploration, or MMX, aim to collect samples from Phobos and return them to Earth for analysis. By examining the composition of these samples, researchers hope to determine whether Phobos and Deimos are captured asteroids, remnants of a giant impact, or something entirely different. The story of Phobos and Deimos is far from over. These tiny moons hold secrets that could reshape our understanding of Mars' history and the processes that shape planetary systems. As we continue to explore them, we may uncover answers to questions that have puzzled scientists for generations. Next, we'll dive into another Martian mystery, the strange, spider-like formations that appear in the planet's south polar region and the fascinating science behind them. Now, let's shift our gaze to the south polar region of Mars, where one of the most bizarre and visually striking phenomena on the red planet unfolds: the so-called Martian spiders. These formations, which resemble sprawling, arachnid-like patterns etched into the surface, are unlike anything found on Earth. They appear seasonally, adding to the mystery of their origin and behavior. The Martian spiders are actually clusters of dark, branching channels that radiate outward from a central point, creating a spider-like appearance when viewed from above. These formations can span hundreds of meters across and are most prominent during the Martian spring, when the polar ice caps begin to thaw. But what causes these eerie patterns to emerge? The leading theory points to a process unique to Mars' sublimation of carbon dioxide ice. During the Martian winter, temperatures in the south polar region drop low enough for carbon dioxide, or dry ice, to freeze directly onto the surface. As spring arrives and sunlight returns, this CO2 ice begins to sublimate, transforming directly from a solid into a gas without passing through a liquid phase. This process creates pressure beneath the ice, which eventually escapes by cracking the surface and erupting in geyser-like jets of gas. As the gas escapes, it carries dark dust and debris from below, depositing it in fan-like patterns around the cracks. Over time, these deposits form the intricate spider-like channels we observe. What makes this phenomenon truly unique is that it's a process that can't occur on Earth. Our planet's atmosphere and temperature conditions don't allow for the formation of large quantities of carbon dioxide ice, let alone its sublimation in such dramatic fashion. On Mars, however, the thin atmosphere and extreme cold create the perfect environment for this otherworldly spectacle. The Martian spiders aren't just a curiosity, they also provide valuable insights into the planet's climate and geology. By studying these formations, scientists can learn more about the seasonal cycles of Mars, the behavior of its polar ice caps, and the interactions between its surface and atmosphere. These patterns are a testament to the dynamic and ever-changing nature of the red planet, even in its frozen polar regions. As we continue to explore Mars, the spiders serve as a reminder of how much we still have to learn about this enigmatic world. Next, we'll delve into another fascinating mystery: the detection of Marsquarks by NASA InSight lander, and what these tremors reveal about the planet's internal structure. Moving from the icy mysteries of the Martian spiders, we now turn our attention to the ground beneath our feet, or rather, beneath the InSight lander's feet. One of the most groundbreaking discoveries in recent years has been the detection of Mars-Quark's seismic tremors that shake the red planet's surface. These quakes, captured by NASA InSight mission, have opened a new window into understanding Mars' internal structure and geological activity. When the InSight lander touched down on Mars in November 2018, it carried with it a highly sensitive seismometer designed to listen for the planet's heartbeat. What it found was surprising. Mars quarks are far more frequent than scientists initially anticipated. Unlike Earth, where tectonic plates constantly shift and grind, Mars was thought to be a geologically quiet world. But the data told a different story. Over the course of its mission, InSight detected hundreds of Mars quarks, ranging from faint tremors to more significant events that shook the planet's surface. So, what causes these quakes on a planet without active plate tectonics? The leading theory suggests that Mars is still cooling and contracting from its formation billions of years ago. As the planet cools, its crust shrinks and cracks, releasing energy in the form of seismic waves. Some quakes may also be triggered by the weight of massive volcanoes like Olympus Mons, which exert pressure on the planet's crust. These findings challenge our understanding of Mars as a static, unchanging world, revealing it to be far more dynamic than we once believed. But studying Mars quarks isn't just about understanding what causes them, it's also about piecing together the puzzle of Mars' internal structure. By analyzing the seismic waves generated by these quakes, scientists can map the planet's interior, much like how an ultrasound creates an image of the human body. This has led to some fascinating discoveries, such as the presence of a molten outer core and a surprisingly thick crust. These insights are helping researchers piece together the story of how Mars formed and evolved over billions of years. However, studying Mars quarks on Mars comes with its own set of challenges. The planet's thin atmosphere and lack of oceans mean that seismic waves behave differently than they do on Earth, making them harder to detect and interpret. Additionally, the InSight lander's seismometer is located in just one spot, limiting our ability to get a complete picture of the planet's seismic activity. Despite these hurdles, the data collected so far has been invaluable, offering a glimpse into the inner workings of a world that continues to surprise us. Mars quarks are more than just geological curiosities. They're a key to unlocking the secrets of Mars' past and present. As we continue to analyze the data from InSight, we're learning not only about the red planet, but also about the processes that shape rocky worlds across the universe. Next, we'll explore another intriguing phenomenon, the towering dust devils that sweep across Mars' surface, leaving behind trails of mystery and wonder. Now, let's shift our gaze from the ground-shaking Mars quarks to the skies of Mars, where another fascinating phenomenon takes center stage: the towering dust devils. These swirling columns of dust, often reaching heights of several kilometers, are a common sight on the red planet, and they play a surprising role in the ongoing exploration of Mars. Dust devils on Mars are not just visually striking, they're also incredibly useful. For the rovers exploring the planet's surface, these whirlwinds act as natural cleaning crews. Over time, Martian dust accumulates on the solar panels of rovers like Opportunity and Spirit, reducing their ability to generate power. But when a dust devil passes by, it can sweep away this layer of dust, giving the rovers a much-needed boost in energy. In fact, some of the longest-lasting rovers owe their extended missions to these fortuitous encounters with dust devils. But how do these towering whirlwinds form in Mars' thin atmosphere, which is only about 1% as dense as Earth? On Earth, dust devils are created when the sun heats the ground, causing warm air to rise rapidly and spin due to wind shear. On Mars, the process is similar but amplified by the planet's unique conditions. The thin atmosphere allows the surface to heat up quickly, creating strong updrafts that can lift dust particles high into the air. These particles are then caught in swirling winds, forming the iconic dust devils we observe. What's particularly intriguing is the scale of these Martian dust devils. Some can reach heights of up to 8 kilometers, far taller than any dust devil on Earth. Their towering size is a result of Mars' lower gravity and thinner atmosphere, which allow the whirlwinds to grow to incredible heights. Yet, despite their size, these dust devils are relatively gentle compared to their earthly counterparts, with wind speeds that rarely exceed 100 kilometers per hour. The persistence of dust devils on Mars also raises questions about the planet's weather patterns. Unlike Earth, where dust devils are short-lived and localized, Martian dust devils can last for hours and travel great distances. This has led scientists to wonder how these whirlwinds interact with the planet's global dust storms, which can engulf the entire planet for months at a time. Are dust devils a precursor to these massive storms, or do they play a role in redistributing dust across the surface? These are questions that remain unanswered, adding to the mystery of Mars' dynamic atmosphere. As we continue to study these enigmatic whirlwinds, we gain not only a deeper understanding of Mars' weather but also valuable insights into how dust and wind shape the planet's surface. Dust devils are more than just a spectacle, they're a key piece of the puzzle in unraveling the red planet's atmospheric secrets. Next, we'll venture to the poles of Mars, where the planet's icy caps hold their own set of mysteries waiting to be uncovered. Now, let's journey to the poles of Mars, where the planet's icy crowns hold secrets as ancient as the red planet itself. The Martian ice caps are a striking feature, composed of layers of ice and dust that have accumulated over millions of years. These polar regions are not just frozen wastelands, they are dynamic, ever-changing landscapes that offer clues about Mars' climate history and its potential for harboring life. The Martian ice caps are made up of two main components, water ice and frozen carbon dioxide, also known as dry ice. During the winter months, temperatures at the poles drop so low that carbon dioxide from the atmosphere freezes directly onto the surface, creating a thick layer of dry ice. In the summer, this layer sublimates, turning directly from ice to gas, revealing the underlying water ice. This seasonal cycle of freezing and sublimation creates a mesmerizing pattern of growth and retreat, making the ice caps one of the most dynamic features on Mars. But what's truly fascinating is the layered structure of these ice caps. Scientists believe that the alternating bands of ice and dust are like pages in a history book, recording changes in Mars' climate over time. Each layer represents a different era, with variations in dust content and ice composition reflecting shifts in the planet's atmosphere and weather patterns. By studying these layers, researchers hope to uncover the story of how Mars transitioned from a warmer, wetter world to the cold, dry planet we see today. Yet, the Martian ice caps are not just relics of the past, they are also active participants in the planet's present-day climate. The size and shape of the ice caps change dramatically with the seasons, expanding in winter and shrinking in summer. But there's a mystery here. Over longer timescales, the ice caps have shown unexplained variations in their size and shape. Some years they grow larger than expected, while in others they shrink more than usual. What's causing these fluctuations? Is it due to changes in Mars' orbit, shifts in its atmosphere, or something else entirely? These questions remain unanswered, adding another layer of intrigue to the Martian poles. The ice caps also play a crucial role in Mars' water cycle. While most of the planet's surface is bone dry, the polar regions hold vast reserves of water ice. If melted, this ice could cover the entire planet in a shallow ocean. This raises tantalizing questions about the potential for life on Mars. Could microbial organisms survive in the icy layers, shielded from the harsh surface conditions? And if so, what might they tell us about the possibility of life elsewhere in the universe? As we continue to study the Martian ice caps, we uncover not only the secrets of the red planet's past but also clues about its future. These icy regions are more than just frozen deserts, they are windows into Mars' climate, geology, and potential for life. Next, we'll turn our attention to another atmospheric mystery, the strange and beautiful auroras that light up the Martian sky. Now, let's shift our gaze from the icy poles to the skies above, where another Martian mystery unfolds: auroras. Unlike the dazzling light shows we see on Earth, Martian auroras are a unique phenomenon that challenges our understanding of planetary atmospheres. Discovered by spacecraft orbiting Mars, these auroras are not only beautiful but also scientifically puzzling, offering clues about the red planet's past and present. On Earth, auroras are created when charged particles from the Sun collide with our planet's magnetic field, funneling energy toward the poles and lighting up the night sky. But Mars is different. It lacks a global magnetic field like Earth's, which raises the question, how do auroras form on Mars? The answer lies in the planet's patchy magnetic fields, remnants of its ancient magnetic past. These localized fields, scattered across the Martian surface, interact with solar particles, creating auroras that are not confined to the poles but can appear almost anywhere on the planet. What makes Martian auroras even more intriguing is their variety. Scientists have identified three main types: diffuse auroras, which spread across large areas of the sky; discrete auroras, which are more localized and intense; and proton auroras, caused by interactions with hydrogen atoms in the upper atmosphere. Each type reveals a different aspect of Mars' atmospheric dynamics, helping researchers piece together the complex interactions between the planet's atmosphere and the solar wind. But the mystery doesn't end there. Unlike Earth's auroras, which are primarily green and red due to oxygen and nitrogen in our atmosphere, Martian auroras are thought to be ultraviolet, invisible to the human eye. This makes them detectable only by specialized instruments, adding another layer of complexity to their study. Why do these auroras form in such a unique way, and what do they tell us about Mars' atmospheric composition and history? These are questions that continue to puzzle scientists. The implications of Martian auroras go beyond their beauty. By studying them, researchers can learn more about how Mars lost its once thick atmosphere and how solar radiation continues to shape the planet today. These auroras also provide insights into the potential habitability of Mars, as they reveal how the planet's atmosphere interacts with space weather, a critical factor for any future human missions. As we unravel the secrets of Martian auroras, we gain not only a deeper understanding of the red planet, but also a broader perspective on how planetary atmospheres evolve. Next, we'll explore another atmospheric enigma: the strange high-altitude clouds that drift across the Martian sky, adding yet another layer of mystery to this fascinating world. Now, let's turn our attention to the skies of Mars, where another atmospheric puzzle awaits: high-altitude clouds. These Martian clouds are unlike anything we see on Earth, adding yet another layer of intrigue to the red planet's already mysterious atmosphere. Floating high above the surface, these clouds are not just a visual spectacle but also a scientific enigma, offering clues about Mars' weather patterns and atmospheric dynamics. On Earth, clouds form when water vapor condenses into tiny droplets or ice crystals, but Mars' thin atmosphere and low temperatures make cloud formation a far more complex process. The Martian clouds are composed primarily of water ice and carbon dioxide ice, also known as dry ice. What's fascinating is that these clouds can form at altitudes of up to 100 kilometers, much higher than any clouds on Earth. This raises the question, how do these clouds form in such a thin atmosphere, and what keeps them suspended at such extreme heights? One leading theory suggests that these high-altitude clouds are created through a process called nucleation, where tiny particles of dust or other materials act as seeds for ice crystals to form around. These particles could come from Martian dust storms, volcanic activity, or even micrometeorites. Once formed, the clouds are carried by winds that sweep across the planet, creating intricate patterns that can stretch for hundreds of kilometers. But the exact mechanisms behind their formation and persistence remain a mystery, as Mars' atmosphere is far less dense and more unpredictable than Earth. What makes these clouds even more intriguing is their role in Mars' weather patterns. Unlike Earth, where clouds play a significant role in regulating temperature and precipitation, Martian clouds have a more subtle but still important influence. They can reflect sunlight, cooling the surface below, or trap heat, creating localized warming effects. This delicate balance affects everything from dust storm activity to the planet's overall climate, making these clouds a key piece of the puzzle in understanding Mars' atmospheric behavior. Another curious aspect of Martian clouds is their appearance. Some are wispy and faint, while others are thick and dense, casting shadows on the surface below. Observations from rovers and orbiters have even captured clouds that shimmer with iridescent colors, a phenomenon caused by the scattering of sunlight through tiny ice crystals. These stunning displays not only captivate our imagination, but also provide valuable data for scientists studying the composition and structure of Mars' atmosphere. As we continue to study these high-altitude clouds, we uncover more questions than answers. Why do they form in certain regions and not others? How do they interact with Mars' dust storms and seasonal changes? And what can they tell us about the planet's past climate and potential for future habitability? These clouds are more than just a beautiful feature of the Martian sky. They are a window into the complex and ever-changing nature of the red planet's atmosphere. Next, we'll descend from the skies to explore another mysterious feature of Mars, the potential cave entrances scattered across its surface, which could hold secrets about the planet's geology and even its potential to harbor life. Now, let's shift our gaze from the skies to the surface of Mars, where another intriguing mystery lies hidden beneath the rocky terrain Martian caves. These potential cave entrances, discovered through images captured by orbiters, have sparked both excitement and curiosity among scientists and space enthusiasts alike. Could these dark, shadowy openings hold secrets about Mars' geological history, or even provide shelter for future human missions? The possibilities are as vast as the caves themselves. The discovery of these cave-like features began with high-resolution images from spacecraft like the Mars Reconnaissance Orbiter. These images revealed unusual, circular depressions on the surface, often surrounded by collapsed material, suggesting the presence of underground voids. Some of these entrances lead to what appear to be extensive lava tubes, natural tunnels formed by ancient volcanic activity. On Earth, similar lava tubes exist, but on Mars, they could be much larger, with some estimates suggesting they could stretch for kilometers. This raises the question, what lies within these mysterious caverns? One of the most compelling aspects of Martian caves is their potential to serve as natural shelters for future human explorers. Mars' surface is bombarded by harmful radiation from the sun and cosmic rays, making long-term exposure dangerous for astronauts. Caves, with their thick layers of rock overhead, could provide a safe haven, shielding humans from these hazards. Additionally, these underground spaces might offer stable temperatures, protecting equipment and supplies from the extreme temperature swings on the surface. But before we can consider using them, we need to understand their structure and stability, tasks that are far from simple. Exploring these caves presents significant challenges. Unlike Earth, where we can send teams of spelunkers or advanced robots to investigate underground spaces, Mars' harsh environment and remote location make such missions incredibly difficult. Current rovers and landers are not designed to navigate steep, rocky terrain or descend into dark, uncharted caverns. Even if we could send a rover inside, communication with Earth would be limited, as the thick rock walls could block signals. This means any exploration would require highly autonomous robots, capable of making decisions on their own, a technological hurdle we're still working to overcome. Beyond their practical uses, Martian caves hold scientific intrigue. They could preserve clues about the planet's volcanic past, offering insights into its geological evolution. Some scientists speculate that these caves might even harbor traces of ancient microbial life, protected from the harsh surface conditions. If life ever existed on Mars, these underground environments could have provided the perfect refuge with stable temperatures and potential access to water ice. Exploring these caves could bring us closer to answering one of humanity's biggest questions. Are we alone in the universe? As we continue to study these enigmatic features, we're left with more questions than answers. How deep do these caves go? Are they connected to larger underground networks? And what secrets might they hold about Mars' past or its future? These caves are more than just geological curiosities. They are potential gateways to understanding the red planet in ways we've only begun to imagine. Next, we'll journey to another fascinating feature of Mars, the ancient riverbeds and deltas that hint at a time when water once flowed freely across its surface. Now, let's turn our attention to the remnants of a time when Mars might have looked strikingly different from the barren world we see today, the ancient riverbeds and deltas that crisscross its surface. These features, etched into the Martian landscape, tell a story of flowing water, a vital ingredient for life as we know it. But how did these riverbeds form on a planet that now appears so dry and desolate? The answer lies in the distant past, when Mars may have been a much wetter and more dynamic world. The discovery of these riverbeds and deltas came from detailed images captured by orbiters and rovers, revealing winding channels and fan-shaped deposits that closely resemble those formed by rivers and lakes on Earth. Some of these features stretch for hundreds of kilometers, with branching patterns that suggest they were carved by persistent water flow over long periods. The presence of deltas, where rivers once emptied into ancient lakes or seas, further strengthens the case for a watery past. These findings have led scientists to believe that Mars may have once had a climate capable of sustaining liquid water on its surface, a tantalizing possibility that raises questions about the planet's history and potential for life. But the mystery deepens when we consider the stark contrast between Mars' past and present. Today, the planet's thin atmosphere and freezing temperatures make it impossible for liquid water to exist on the surface for long. So how did these riverbeds and deltas form? One leading theory suggests that Mars experienced periods of warmer, wetter conditions billions of years ago, possibly due to a thicker atmosphere and volcanic activity that released greenhouse gases. These conditions could have allowed rivers to flow and lakes to form, shaping the landscape we see today. However, as the planet's atmosphere thinned and its climate cooled, the water either froze, evaporated, or retreated underground, leaving behind the dry riverbeds as silent witnesses to a bygone era. The implications of these ancient water features are profound. If Mars once had flowing rivers and stable bodies of water, it raises the possibility that the planet could have supported life. Water is essential for life as we know it, and the presence of riverbeds and deltas suggests that Mars may have had the right conditions for microbial life to emerge and thrive. Some scientists even speculate that these ancient waterways could have carried organic materials, creating environments where life could have taken hold. Exploring these features could provide crucial clues about Mars' habitability and whether life ever existed there. Yet, the formation of these riverbeds and deltas remains a puzzle. While the evidence points to flowing water, the exact mechanisms that created these features are still debated. Did water flow continuously, or were there episodic bursts of activity, such as flash floods or seasonal melting? Could underground water sources have played a role, seeping to the surface and carving out channels over time? These questions highlight the complexity of Mars' geological history and the challenges of piecing together its past from the clues left behind. As we continue to study these ancient riverbeds and deltas, we're reminded of how much we still have to learn about Mars. These features are not just relics of a distant past. They are windows into a time when the red planet may have been a very different place, a world with rivers, lakes, and perhaps even life. Each discovery brings us closer to understanding the story of Mars and its place in the broader narrative of our solar system. Next, we'll explore another intriguing mystery, the discovery of glass deposits in Martian craters and what they might reveal about the planet's history and potential for preserving signs of ancient life. Now, shifting our focus to another fascinating discovery, let's delve into the enigmatic glass deposits found in Martian craters. These deposits, detected by orbiting spacecraft and rovers, have sparked significant interest among scientists due to their unique properties and potential implications for understanding Mars' history. Glass formed under extreme heat is not something you'd typically expect to find scattered across a cold, dusty planet like Mars. Yet there it is, hidden within the scars of ancient impacts. The discovery of Martian glass came as a surprise. Using advanced instruments, researchers identified deposits of impact glass in several craters, formed when meteorites struck the planet's surface with such force that they melted the surrounding rock. This molten material quickly cooled, creating glass. On Earth, similar impact glass has been found to preserve delicate organic materials and even microbial life, offering a kind of time capsule from the past. This raises an exciting possibility. Could Martian glass also hold traces of ancient life? If Mars once harbored microbial organisms, these glass deposits might have trapped and preserved them, providing a rare opportunity to uncover evidence of life that existed billions of years ago. But how did these glass deposits form on Mars? The process likely began with violent meteorite impacts, which generated immense heat and pressure, melting the surface rocks. As the molten material rapidly cooled in the planet's thin atmosphere, it solidified into glass. What makes this phenomenon particularly intriguing is the sheer scale of some of these deposits. In certain craters, the glass appears to be widespread, suggesting that large-scale impacts were once a common occurrence on Mars. This not only sheds light on the planet's geological history, but also hints at the extreme conditions that shaped its surface over time. The significance of Martian glass extends beyond its potential to preserve ancient life. These deposits could also serve as valuable resources for future human missions to Mars. Glass can be used to create building materials, tools, and even protective coatings for habitats, making it a practical asset for colonization efforts. Additionally, studying these deposits could help scientists better understand the frequency and intensity of meteorite impacts on Mars, providing insights into the planet's past and its interactions with the solar system. However, the mystery of Martian glass doesn't end with its formation. Scientists are still puzzled by how these deposits have survived for so long without being eroded or buried by dust. Mars' harsh environment, with its constant dust storms and temperature fluctuations, would seem to make preservation difficult. Yet, the glass remains intact, offering a tantalizing glimpse into the planet's distant past. This durability suggests that these deposits could be key to unlocking some of Mars' most closely guarded secrets. As we continue to explore the red planet, the discovery of Martian glass serves as a reminder of how much we still have to learn. These deposits are not just geological curiosities, they are potential windows into Mars' ancient history and its capacity to support life. Each new finding brings us closer to answering the ultimate question: was Mars ever home to life? And if so, could these glass deposits hold the evidence we've been searching for? Next, we'll turn our attention to another electrifying mystery: the detection of lightning-like discharges in Martian dust storms and what they reveal about the planet's atmospheric dynamics. Now, let's illuminate another electrifying mystery on Mars: the detection of lightning-like discharges during its massive dust storms. Unlike the familiar bolts of lightning we see on Earth, these Martian discharges are a peculiar phenomenon, sparking curiosity about how they form in the planet's thin atmosphere. Martian lightning was first detected by orbiting spacecraft and later confirmed by ground-based instruments. These discharges are not the dramatic, sky-splitting bolts we associate with thunderstorms on Earth. Instead, they are smaller, more subtle, and often described as glow discharges or sparks. They occur within the swirling dust storms that can engulf the entire planet, creating a spectacle that is both fascinating and puzzling. The mystery lies in how these discharges happen at all. Mars' atmosphere is incredibly thin, about 100 times less dense than Earth's. This makes it difficult for the electrical charges needed for lightning to build up. On Earth, lightning is generated when ice particles and water droplets collide within clouds, creating static electricity. But on Mars, there's no liquid water or ice in the atmosphere to facilitate this process. So, what's causing these discharges? Scientists believe the answer may lie in the dust itself. As dust particles are lifted into the atmosphere during storms, they collide and rub against each other, generating static electricity. This process, known as triboelectric charging, could create enough charge separation to produce the faint discharges observed. However, the exact mechanism remains unclear. Why do these discharges appear so different from Earth's lightning, and how do they persist in such a thin atmosphere? These questions continue to challenge researchers. The implications of Martian lightning are significant. For one, these discharges could affect the planet's atmospheric chemistry, potentially creating reactive compounds that influence the environment. They might also pose risks to future human missions, as even small electrical discharges could interfere with equipment or pose hazards to astronauts. Understanding this phenomenon is not just about solving a scientific puzzle, it's about preparing for the challenges of exploring and potentially living on Mars. What makes this mystery even more intriguing is its connection to Mars' weather patterns. Dust storms on Mars are not just local events. They can grow to cover the entire planet, lasting for weeks or even months. These storms play a crucial role in shaping the planet's climate, and the presence of lightning-like discharges adds another layer of complexity to our understanding of Martian weather. Could these discharges be a key to unlocking the secrets of Mars' atmospheric dynamics? As we continue to study the red planet, the discovery of Martian lightning reminds us of how much we still have to learn. Each new observation brings us closer to understanding the unique processes that shape this alien world. And while the mystery of Martian lightning remains unsolved, it serves as a powerful reminder of the surprises that await us as we explore the cosmos. Next, we'll uncover another intriguing feature of Mars, the discovery of salt deposits and what they reveal about the planet's watery past. Shifting our focus to another fascinating discovery, let's delve into the enigmatic salt deposits scattered across the Martian surface. These deposits, detected by rovers and orbiters alike, are more than just geological curiosities. They are potential windows into Mars' watery past and its capacity to support life. The discovery of salt deposits on Mars has sparked significant interest among scientists. These deposits, primarily composed of minerals like chlorides and sulfates, are often found in regions that show signs of ancient water activity. Their presence suggests that liquid water once flowed or pooled on the planet's surface, leaving behind these mineral remnants as it evaporated. But how exactly did these deposits form? One leading theory is that they are the remnants of ancient lakes or seas. As water evaporated, it left behind concentrated salts, much like the salt flats we see on Earth, such as the Bonneville Salt Flats in Utah. On Mars, these deposits are often found in low-lying areas, such as craters or basins, where water might have collected billions of years ago. The sheer scale of some of these deposits hints at the possibility of vast, long-lasting bodies of water, environments that could have been hospitable to microbial life. However, the mystery deepens when we consider the conditions required for these deposits to form. On Earth, salt deposits often form in arid environments with high evaporation rates. But Mars' atmosphere is far thinner and colder than Earth's, raising questions about how these processes could have occurred. Did Mars once have a thicker atmosphere that allowed for more stable liquid water? Or did these deposits form under unique, short-lived conditions? these questions remain unanswered, adding to the intrigue of Mars' geological history. The implications of these salt deposits are profound. If they indeed formed in the presence of liquid water, they could mark regions where life might have once thrived. Salt is known to preserve organic material, and on Earth, ancient salt deposits have been found to contain microbial fossils. Could the same be true for Mars? Future missions equipped with advanced instruments might one day analyze these deposits for signs of past life, turning speculation into scientific fact. Moreover, these deposits could play a crucial role in future human exploration. Salt is a valuable resource, potentially useful for producing oxygen, water, or even building materials. Understanding their distribution and composition could help identify ideal locations for future bases or resource extraction. As we piece together the story of Mars' salt deposits, we're reminded of the planet's dynamic and complex history. These mineral remnants are more than just geological features. They are clues to a time when Mars might have been a very different world, one that could have supported life. And as we continue to explore, each discovery brings us closer to unraveling the mysteries of the Red Planet. Next, we'll turn our attention to another puzzling aspect of Mars, the patchy magnetic fields that hint at the planet's lost dynamo and its implications for its ancient atmosphere. Now, let's venture into one of the most intriguing mysteries of Mars, its patchy magnetic fields. Unlike Earth, which boasts a strong, global magnetic field generated by its molten core, Mars presents a far more fragmented picture. These scattered magnetic fields, detected by orbiters like Mars Global Surveyor, are concentrated in certain regions of the planet's crust, creating a patchwork of magnetic anomalies. But what do these magnetic fields tell us about Mars' past, and why did the planet lose its original planet-wide magnetic field? The story begins billions of years ago, when Mars is believed to have had a global magnetic field similar to Earth. This field would have been generated by a dynamo effect, a process driven by the movement of molten iron in the planet's core. A global magnetic field acts as a shield, protecting a planet's atmosphere from the relentless bombardment of solar wind, the stream of charged particles emitted by the sun. On Earth, this magnetic shield is crucial for maintaining our atmosphere and, by extension, life as we know it. But something happened to Mars. At some point in its history, the planet's dynamo shut down and its global magnetic field faded away. The result, Mars' atmosphere was stripped away over time, leaving the planet cold, dry, and exposed to the harsh conditions of space. Today, the remnants of this once powerful magnetic field are locked in the planet's crust, preserved in magnetized rocks that formed when Mars still had an active dynamo. These rocks act like tiny magnets, creating the patchy magnetic fields we observe today. The question that baffles scientists is, why did Mars lose its magnetic field? One leading theory suggests that the planet's core cooled and solidified, halting the dynamo process. Another possibility is that a massive impact, like the one that created the planet's enormous Borealis basin, disrupted the core's dynamics. Without a magnetic shield, Mars' atmosphere was vulnerable to erosion by solar wind, leading to the thin, inhospitable atmosphere we see today. The implications of this loss are profound. Without a global magnetic field, Mars became a far less hospitable place, with its surface exposed to harmful radiation and its climate shifting dramatically. This raises another tantalizing question. Could the loss of the magnetic field have played a role in the disappearance of any potential Martian life? While we don't yet have the answers, studying these patchy magnetic fields offers clues about Mars' ancient environment and its transformation over billions of years. As we continue to explore Mars, understanding its magnetic history remains a key piece of the puzzle. These patchy fields are not just remnants of a bygone era. They are windows into a time when Mars might have been a very different world, one with a protective magnetic shield and a thicker, warmer atmosphere. And as we uncover more about these magnetic anomalies, we inch closer to understanding the fate of the red planet and its potential for life, past or present. Next, we'll turn our attention to another fascinating feature of Mars, the gullies that line its slopes resembling water-carved formations on Earth, and the ongoing debate about their origins. Now, shifting our gaze to the Martian surface, we encounter another captivating mystery: the gullies that snake down the planet's slopes. These formations, strikingly similar to water-carved gullies on Earth, have sparked intense debate among scientists about their origins and what they might reveal about Mars' past. The Martian gullies were first discovered in high-resolution images captured by the Mars Global Surveyor in the late 1990s. These features appear as narrow channels, often accompanied by alcoves at their tops and fan-shaped deposits at their bases. At first glance, they look remarkably like the gullies formed by flowing water on Earth, leading many to speculate that liquid water might still exist on Mars, at least intermittently. But here's where the mystery deepens. While water is a leading candidate for carving these gullies, the conditions on Mars make this explanation far from straightforward. The planet's thin atmosphere and freezing temperatures mean that liquid water would either evaporate or freeze almost instantly on the surface. So, if water is responsible, how could it flow long enough to carve these features? One theory suggests that the gullies might be formed by seasonal melting of subsurface ice. During warmer periods, this ice could melt, creating brief bursts of liquid water that carve the gullies before freezing again. Another possibility is that carbon dioxide, rather than water, plays a key role. On Mars, carbon dioxide can freeze directly into solid form during the winter, creating a layer of dry ice. When this ice sublimates, turning directly from solid to gas, it could trigger small landslides or flows of debris, mimicking the appearance of water-carved gullies. Adding to the intrigue, some gullies appear to be active, with changes observed over time. Images taken years apart show new deposits and altered channels, suggesting that these features are still evolving. This activity raises even more questions. Are these changes caused by water, carbon dioxide, or some other process entirely? The debate over the Martian gullies is far from settled, and each new discovery adds another layer of complexity. What's clear, however, is that these features hold valuable clues about the planet's geological and climatic history. Whether formed by water, carbon dioxide, or another mechanism, the gullies remind us that Mars is a dynamic world still capable of surprising us. As we continue to explore these enigmatic features, we're not just studying the gullies themselves, we're piecing together the story of a planet that may have once been far more Earth-like than it appears today. And with every new observation, we come closer to understanding the forces that shape Mars, both past and present. Next, we'll turn our attention to one of the most iconic features of the red planet, its massive volcanoes, including Olympus Mons, and the mystery of why they grew so much larger than any volcano on Earth. Now, let's turn our attention to one of the most awe-inspiring features of the red planet, its colossal volcanoes. Among these giants, Olympus Mons stands out as the largest volcano in the solar system, towering at nearly 22 kilometers high, more than 2.5 times the height of Mount Everest. But what makes these Martian volcanoes so massive, and why do they dwarf anything we see on Earth? The answer lies in the unique geology of Mars. Unlike Earth, Mars lacks the tectonic plate activity that constantly reshapes our planet's surface. On Earth, the movement of tectonic plates creates a dynamic environment where volcanoes form, erupt, and eventually become inactive as the plates shift. But on Mars, the crust remains stationary, allowing magma to build up in the same spot over billions of years. This lack of plate movement means that Martian volcanoes can grow to staggering sizes without being disrupted or eroded away. Olympus Mons, for example, is not just tall, it's also incredibly wide, spanning over 600 kilometers in diameter. To put that into perspective, it's roughly the size of the state of Arizona. Its slopes are relatively gentle, with an average incline of just 5 degrees, making it more of a shield volcano, similar to Hawaii's Mauna Loa but on a much grander scale. But the mystery doesn't end with their size. Scientists are still puzzled by the sheer longevity of these volcanoes. On Earth, volcanic activity tends to be episodic, with periods of intense eruptions followed by long stretches of dormancy. On Mars, however, evidence suggests that some volcanoes, like Olympus Mons, may have been active for hundreds of millions of years, if not longer. This raises the question, what fueled such prolonged volcanic activity on a planet that's now geologically quiet? One theory points to Mars' lower gravity, which allows magma to rise more easily to the surface, creating larger and longer-lasting eruptions. Another possibility is that the planet's mantle, the layer beneath the crust, was once much hotter and more active, providing a steady supply of magma to feed these volcanic giants. Adding to the intrigue, the sheer size of these volcanoes has implications for Mars' climate and atmosphere. Massive eruptions could have released vast amounts of gases, potentially warming the planet and creating conditions more favorable for liquid water in the past. This connection between volcanic activity and habitability makes studying these features crucial for understanding Mars' history. As we continue to explore these towering landmarks, we're not just marveling at their size, we're uncovering clues about the forces that shaped Mars and the potential for life in its distant past. Next, we'll venture into another striking feature of the Red Planet, its vast canyons, including the colossal Valles Marineris, and the mystery of how they became so much larger than anything on Earth. Now, shifting our gaze from the towering volcanoes, we arrive at another breathtaking feature of Mars, its vast canyons. Among these, Valles Marineris stands as the crown jewel, a colossal canyon system that stretches over 4,000 kilometers long, up to 200 kilometers wide, and plunges as deep as 7 kilometers in some areas. To put that into perspective, if Valles Marineris were on Earth, it would span the entire length of the United States from coast to coast, dwarfing even the Grand Canyon, which seems almost modest in comparison. But how did such an enormous canyon system form on Mars? The answer lies in a combination of geological forces that are both familiar and alien. On Earth, canyons like the Grand Canyon are primarily carved by the relentless flow of water over millions of years. While water may have played a role in shaping parts of Valles Marineris, the canyon's formation is largely attributed to tectonic activity. Billions of years ago, as Mars' crust cooled and contracted, it cracked and split, creating massive fractures. Over time, these fractures were widened and deepened by a combination of erosion, landslides, and possibly even ancient floods. What makes Valles Marineris so unique, however, is its sheer scale. Unlike Earth's canyons, which are shaped by the slow and steady processes of erosion, Valles Marineris appears to have been formed by more dramatic and catastrophic events. Some scientists believe that the canyon's formation was accelerated by the planet's lower gravity, which allowed for larger and more frequent landslides. Others suggest that volcanic activity in the nearby Tharsis region, home to Olympus Mons, may have played a role by causing the crust to stretch and crack, further widening the canyon. Adding to the mystery, Valles Marineris is not just a single canyon but a complex network of interconnected chasms, cliffs, and valleys. Some sections, like the Coprates Chasma, are so deep and steep that they could easily swallow entire mountain ranges. Others, like the Ophir Chasma, feature layered rock formations that hint at a history of repeated flooding and sedimentation. These layers are like pages in a book, preserving clues about Mars' ancient climate and the forces that shaped its surface. One of the most intriguing questions surrounding Valles Marineris is why it grew so much larger than any canyon on Earth. Part of the answer lies in Mars' lack of plate tectonics. On Earth, the movement of tectonic plates constantly reshapes the surface, limiting the size and lifespan of geological features. But on Mars, the absence of such activity allowed Valles Marineris to grow uninterrupted for billions of years, creating a feature that is not only massive but also remarkably well preserved. As we continue to study these Martian canyons, we're not just marveling at their size, we're uncovering clues about the planet's geological history and its potential to have once supported life. The layers of rock within Valles Marineris, for example, could hold evidence of ancient water flows or even microbial life, and the canyon's sheer size offers a window into the forces that shaped Mars into the world we see today. Next, we'll turn our attention to another fascinating feature of the red planet, the mysterious frost that appears seasonally on its surface and the questions it raises about Mars' climate and atmosphere. Now, as we move from the colossal canyons of Mars, let's explore a phenomenon that adds a touch of Earth-like familiarity to the red planet, its frost. Yes, frost on Mars. While it might seem surprising, frost has been observed on the Martian surface, appearing seasonally in certain regions, particularly near the poles and in shaded areas. This frost isn't made of water ice like the frost we see on Earth, but is primarily composed of carbon dioxide, also known as dry ice. The discovery of Martian frost dates back to the early observations made by orbiters like the Viking missions, but it wasn't until more recent missions such as NASA's Mars Reconnaissance Orbiter and the European Space Agency's Mars Express that we gained a clearer picture of its behavior. These missions revealed that frost forms during the colder Martian nights, particularly in the winter months, and sublimates, or turns directly from solid to gas as temperatures rise during the day. What makes this frost so intriguing is the mystery of how it forms in Mars' incredibly thin atmosphere. On Earth, frost forms when water vapor in the air condenses and freezes on cold surfaces. But Mars' atmosphere is less than 1% as dense as Earth's, making it far more challenging for frost to accumulate. Scientists believe that the frost on Mars forms through a combination of factors, including the planet's low temperatures, which can drop to -125 degrees Celsius, and the presence of carbon dioxide, which makes up the majority of its atmosphere. The seasonal nature of this frost also provides valuable insights into Mars' climate. During the Martian winter, carbon dioxide from the atmosphere freezes onto the surface, creating a layer of frost that can extend over vast areas. As the seasons change and temperatures rise, this frost sublimates, releasing carbon dioxide back into the atmosphere. This cycle plays a crucial role in the planet's weather patterns, driving winds and even contributing to the formation of dust storms. But the frost isn't just a curiosity, it's a key piece of the puzzle in understanding Mars' past and present climate. By studying its distribution and behavior, scientists can learn more about the planet's atmospheric dynamics and how it has evolved over time. For example, the presence of frost in certain regions suggests that these areas may have once been colder or more humid, offering clues about Mars' ancient climate and its potential to have supported liquid water. Adding to the mystery, some observations have hinted at the possibility of water frost in addition to carbon dioxide frost. While water frost is much rarer and harder to detect, its presence would have significant implications for understanding Mars' water cycle and its potential to support life. As we continue to explore the red planet, the study of Martian frost will remain a vital area of research. It not only helps us understand the planet's current climate, but also provides a window into its past, offering clues about how Mars transformed from a potentially habitable world to the cold, arid planet we see today. Next, we'll delve into another atmospheric phenomenon that shapes the Martian landscape: the planet-wide dust storms that can engulf the entire surface and last for months. Now, shifting our focus from the delicate frost of Mars, let's turn to a phenomenon that showcases the planet's raw power and unpredictability: the Martian dust storms. These storms are not your average earthly weather events. They are colossal, planet-wide tempests that can engulf the entire surface of Mars, lasting for weeks or even months. Imagine a storm so vast it could cover the entire United States, and then some. That's the scale we're talking about here. Martian dust storms are a regular occurrence happening every Martian year, which is roughly equivalent to 2 Earth years. They typically begin in the southern hemisphere during Mars' spring and summer, when the planet is closest to the Sun. The increased solar energy heats the surface, creating strong winds that lift fine dust particles into the atmosphere. Once the dust is airborne, it absorbs even more sunlight, warming the atmosphere further and fueling the storm's growth. What's truly baffling is how these storms can grow to such enormous proportions. On Earth, dust storms are relatively localized and short-lived, but on Mars, a small storm can quickly escalate into a global event, shrouding the entire planet in a thick, reddish haze. Scientists are still trying to understand the mechanisms behind this rapid expansion. One theory suggests that the low atmospheric pressure and gravity on Mars allow dust particles to stay suspended for much longer, enabling storms to grow and persist far beyond what we see on Earth. The intensity of these storms is another mystery. Winds on Mars can reach speeds of up to 100 kilometers per hour, but because the atmosphere is so thin, these winds don't have the same destructive force as hurricanes on Earth. Instead, the real challenge comes from the sheer amount of dust. The fine particles can clog solar panels, reducing the power supply for rovers and landers, and even obscure cameras and scientific instruments. Perhaps the most famous example of a Martian dust storm's impact was the one that brought NASA's Opportunity rover to its end in 2018. The storm was so severe that it blocked sunlight for months, preventing the rover's solar panels from recharging its batteries. Despite efforts to revive it, Opportunity fell silent, marking the end of its remarkable 15-year mission. But dust storms aren't just a hazard for exploration. They also play a significant role in shaping Mars' climate. The dust particles absorb sunlight, warming the atmosphere and driving weather patterns. They can even influence the planet's albedo or reflectivity, which in turn affects global temperatures. By studying these storms, scientists hope to gain a better understanding of Mars' atmospheric dynamics and how they've evolved over time. As we continue to explore the red planet, dust storms remain both a challenge and a source of fascination. They remind us of the harsh and unpredictable nature of Mars, while also offering valuable insights into its climate and history. Next, we'll uncover another hidden feature of Mars, the subsurface ice that lies beneath its surface, waiting to be explored. Now, let's dig beneath the surface literally to uncover one of Mars' most intriguing secrets, the Martian subsurface ice. Hidden beneath the planet's dusty exterior lies vast reservoirs of ice, a discovery that has sparked excitement and curiosity among scientists and space enthusiasts alike. This ice isn't just a scientific curiosity, it could be a game-changer for future missions to the red planet. The detection of subsurface ice on Mars has been made possible through a combination of orbital observations and ground-based measurements. Instruments like NASA's Mars Reconnaissance Orbiter have used radar to map the distribution of ice beneath the surface, revealing that it's not evenly spread but concentrated in specific regions, particularly near the poles and mid-latitudes. These icy deposits are often found just a few meters below the surface, making them potentially accessible for future exploration. But why is this ice so important? For one, it could serve as a critical resource for human missions to Mars. Water is essential for life, and it's also a key ingredient for producing oxygen and rocket fuel. If astronauts can extract and use this ice, it could significantly reduce the cost and complexity of missions, making long-term exploration and even colonization more feasible. Imagine a future where Martian ice is harvested to sustain human habitats and power spacecraft. It's a vision that's closer to reality than you might think. The mystery, however, lies in how this ice formed and why it persists in certain regions. On Earth, subsurface ice is typically found in polar regions or permafrost, where temperatures remain consistently low. But Mars' climate is far more extreme and variable. Some theories suggest that the ice could be remnants of a time when Mars had a thicker atmosphere and flowing water on its surface. Over millions of years, as the planet's climate changed, this water may have frozen and become trapped beneath the surface. Another possibility is that the ice formed through a process called sublimation, where water vapor in the atmosphere freezes directly into the ground. What's even more puzzling is how the ice manages to survive in regions where temperatures fluctuate dramatically. On Mars, the thin atmosphere provides little insulation, allowing surface temperatures to swing from freezing to relatively warm within a single day. Yet somehow the subsurface ice remains stable. Scientists believe that a layer of dust or regolith may act as an insulating blanket, protecting the ice from the extreme temperature changes above. The presence of subsurface ice also raises fascinating questions about Mars' past and potential for life. If liquid water once flowed on the surface, could microbial life have existed, and might it still survive in these icy reservoirs? While we don't have answers yet, the discovery of subsurface ice opens up exciting possibilities for future exploration and scientific discovery. As we continue to probe the mysteries of Mars, the subsurface ice stands as a tantalizing clue to the planet's history and a vital resource for its future. Next, we'll turn our attention to another enigmatic feature of the red planet, the Martian meteorites that have made their way to Earth, offering us a rare glimpse into Mars' distant past. Now, let's shift our gaze from the icy depths of Mars to something that has traveled far beyond its surface: Martian meteorites. These rare fragments of the red planet have made their way to Earth, offering scientists a unique opportunity to study Mars without ever leaving our own planet. But how did these rocks escape Mars' gravity, and what secrets do they hold about its ancient past? Martian meteorites are pieces of the planet that were blasted into space by powerful impacts, such as asteroid collisions or volcanic eruptions. After being ejected, these rocks drifted through space for millions of years before eventually falling to Earth. To date, scientists have identified over 100 meteorites that originated from Mars, each one a time capsule preserving clues about the planet's geology and history. What makes these meteorites so fascinating is their composition. Unlike most meteorites found on Earth, which come from asteroids or comets, Martian meteorites contain minerals and gases that match the data collected by Mars rovers and orbiters. For example, tiny bubbles of gas trapped inside these rocks have been found to match the composition of Mars' atmosphere, as measured by the Viking missions in the 1970s. This definitive link confirms their Martian origin and makes them invaluable for research. But here's where the mystery deepens. Martian meteorites differ significantly from the rocks we've studied on Mars' surface. While rovers like Curiosity and Perseverance have analyzed sedimentary rocks formed in ancient lakes and rivers, Martian meteorites are primarily igneous, meaning they formed from volcanic activity. This discrepancy raises questions about the diversity of Mars' geology and whether these meteorites represent a specific period or region of the planet's history. One of the most famous Martian meteorites, known as Allen Hill's 84001, sparked intense debate in the 1990s when scientists claimed to have found microscopic structures resembling fossilized bacteria. While the evidence remains inconclusive, the discovery ignited discussions about the possibility of past life on Mars and whether similar signs could be found in other meteorites. The study of Martian meteorites also provides insights into the planet's volcanic history. Some of these rocks are billions of years old, dating back to a time when Mars was geologically active. By analyzing their mineral composition, scientists can piece together the timeline of volcanic eruptions and tectonic activity, shedding light on how Mars evolved from a warm, wet world to the cold, dry planet we see today. Yet, despite their scientific value, Martian meteorites also present challenges. Because they were ejected from Mars by violent impacts, they may not represent the planet's surface as a whole. Additionally, the journey through space and entry into Earth's atmosphere can alter their composition, making it harder to draw definitive conclusions. As we continue to explore Mars, both through missions and the study of these meteorites, we gain a clearer picture of the planet's history and its potential for harboring life. These rocks are more than just fragments of another world. They are windows into Mars' past, offering clues that could reshape our understanding of the red planet. Next, we'll delve into another enduring mystery: how Mars lost much of its atmosphere, transforming from a potentially habitable world into the barren landscape we know today. Now, let's turn our attention to one of the most profound mysteries surrounding Mars: the loss of its atmosphere. Billions of years ago, Mars was a very different world. Evidence suggests it had a thicker atmosphere, flowing rivers, and possibly even oceans. But today, the red planet is a cold, barren desert with an atmosphere so thin it's barely a whisper compared to Earth. So, what happened? How did Mars lose so much of its air? And what does this mean for its past and future habitability? The leading theory points to the role of the solar wind, a stream of charged particles constantly flowing from the Sun. Unlike Earth, Mars lacks a global magnetic field to shield its atmosphere from this relentless bombardment. Over time, the solar wind stripped away much of Mars' atmosphere, molecule by molecule. NASA's Methane mission, which has been orbiting Mars since 2014, has provided critical evidence supporting this idea. The spacecraft observed how solar particles interact with the upper atmosphere, accelerating the escape of gases like hydrogen and oxygen into space. But the solar wind isn't the only culprit. Mars' lower gravity also played a significant role. With only about 38% of Earth's gravitational pull, Mars struggled to hold onto its atmosphere. Lighter gases, such as hydrogen, escaped more easily, while heavier gases like carbon dioxide lingered longer but were still vulnerable to being stripped away. Additionally, massive asteroid impacts in Mars' early history may have contributed to atmospheric loss by blasting gases into space during collisions. The implications of this atmospheric loss are staggering. Without a thick atmosphere, Mars couldn't retain heat, causing its surface temperatures to plummet. Liquid water, essential for life as we know it, could no longer exist in stable form. The planet's once potentially habitable environment transformed into the harsh, dry landscape we see today. This raises a haunting question. If Mars once had the conditions to support life, did it have enough time for life to emerge before its atmosphere vanished? Interestingly, some of Mars' atmosphere may still be hiding beneath its surface. Scientists believe that significant amounts of carbon dioxide and water could be trapped in the planet's polar ice caps or locked within minerals in the soil. If future missions can unlock these reservoirs, it might be possible to release these gases and thicken the atmosphere, a concept known as terraforming. While this remains a distant possibility, it offers a glimmer of hope for making Mars more Earth-like in the future. The mystery of Mars' atmosphere loss isn't just about understanding the past, it's also about preparing for the future. As we plan for human exploration and potential colonization of the red planet, understanding how its atmosphere evolved is crucial. It helps us anticipate the challenges of living on a world with such a thin atmosphere and informs strategies for creating sustainable habitats. As we continue to study Mars, both from orbit and on the ground, we're piecing together the story of its atmospheric decline. Each discovery brings us closer to understanding not only what happened to Mars, but also what it means for the search for life beyond Earth. Next, we'll explore another intriguing feature of the red planet: the strange polygonal patterns that dominate its polar regions, offering yet another clue to its complex history. Now, shifting our gaze to the icy expanses of Mars' polar regions, we encounter another fascinating mystery: the Martian polygonal terrain. These intricate geometric patterns stretch across the landscape like a vast natural mosaic, captivating scientists and sparking curiosity about their origins. But what exactly are these polygons, and what do they tell us about Mars' climate and history? The polygonal patterns are formed by the repeated freezing and thawing of ice beneath the surface. During the cold Martian winters, the ground contracts, creating cracks. When warmer temperatures return, the ice expands, pushing the cracks wider and forming the distinct polygonal shapes. This process, known as thermal contraction, is similar to what happens in Earth's Arctic and Antarctic regions, where similar patterns can be found. However, on Mars, these polygons are far more widespread and often much larger, sometimes spanning hundreds of meters across. What makes these formations particularly intriguing is their connection to Mars' climate history. The polygons suggest that the planet's polar regions have experienced significant temperature fluctuations over time. By studying their size, depth, and distribution, scientists can piece together clues about how Mars' climate has evolved. For instance, larger polygons may indicate longer or more intense periods of freezing, while smaller ones could point to more frequent temperature changes. But the mystery doesn't end there. While thermal contraction explains the basic formation of these patterns, the sheer scale and uniformity of the Martian polygons raise questions. Why are they so widespread, and why do they appear in such consistent shapes? Some researchers speculate that the presence of subsurface ice or even liquid water might play a role in shaping these features. Others suggest that the unique composition of Martian soil, rich in salts and minerals, could influence how the polygons form and evolve. The significance of these polygonal terrains extends beyond their aesthetic appeal. They offer a window into Mars' past, revealing how the planet's climate has shifted over millions of years. Understanding these patterns could also provide valuable insights for future missions, particularly those aimed at exploring the polar regions for signs of water or even microbial life. If subsurface ice is indeed involved, these areas could become key targets for human exploration and potential resource extraction. As we continue to study these enigmatic formations, each discovery brings us closer to unraveling the complex story of Mars' climate. The polygonal terrain is more than just a geological curiosity, it's a testament to the dynamic and ever-changing nature of the red planet. Next, we'll delve into another intriguing aspect of Mars' surface, the layered sedimentary rocks that hold secrets to its ancient past and the possibility of life. Now, turning our attention to the Martian surface, we uncover another captivating mystery, the layered sedimentary rocks. These striking formations, resembling the pages of a geological history book, hold secrets that could rewrite our understanding of Mars' ancient past and its potential for life. But how did these layers form in such a dry and seemingly barren environment? And what clues do they offer about the planet's history? The discovery of layered rocks on Mars was a groundbreaking moment for planetary scientists. These formations, often found in regions like Gale Crater and the slopes of Mount Sharp, are composed of alternating bands of sediment, each layer telling a story of a different era in Mars' history. On Earth, sedimentary rocks typically form in environments where water, wind, or ice deposit layers of material over time. The presence of similar structures on Mars suggests that the planet may have once had conditions capable of supporting such processes. One of the most compelling aspects of these layered rocks is their potential to preserve signs of ancient life. On Earth, sedimentary rocks are known to harbor fossils and other evidence of past organisms. Could the same be true for Mars? Scientists believe that if microbial life ever existed on the red planet, these layers might contain traces of it. The minerals within the rocks, such as clays and sulfates, are particularly promising as they often form in the presence of water and can protect organic material from degradation over time. But the mystery deepens when we consider how these layers formed in Mars' current dry environment. The planet's surface today is arid and cold, with liquid water existing only briefly, if at all. Yet, the layered rocks suggest that Mars once had a very different climate, one that could have supported lakes, rivers, or even oceans. Some researchers propose that these layers were deposited by ancient bodies of water that periodically filled and dried up, leaving behind sediments that hardened into rock. Others suggest that wind or volcanic activity might have played a role in shaping these formations. The challenge lies in piecing together the exact processes that created these layers. Each band of sediment represents a snapshot of Mars' environment at a specific point in time. By analyzing their composition, thickness, and arrangement, scientists can reconstruct the planet's climatic and geological history. For example, thicker layers might indicate periods of prolonged water flow, while thinner ones could point to more sporadic events. The presence of certain minerals, like hematite or gypsum, can also provide clues about the conditions under which the layers formed. What makes these layered rocks even more intriguing is their potential to guide future exploration. Areas with well-preserved sedimentary layers are prime targets for missions searching for signs of past life. Rovers like Curiosity and Perseverance have already begun studying these formations, drilling into the rocks to analyze their composition and search for organic molecules. If life ever existed on Mars, these layers might be the key to finding it. As we continue to explore these ancient formations, each layer reveals a new chapter in Mars' story. The layered sedimentary rocks are more than just geological curiosities. They are windows into a time when Mars might have been a very different world, teeming with water and perhaps even life. Next, we'll journey into the Martian night sky to uncover another enigmatic phenomenon, the faint glow that illuminates the darkness and hints at the planet's atmospheric secrets. Now, let's shift our gaze upward, away from the Martian surface and into the enigmatic night sky of the red planet. Here, we encounter a phenomenon that has puzzled scientists and stargazers alike, the Martian night glow. This faint, ethereal glow illuminates the darkness of Mars' nights, offering a glimpse into the planet's atmospheric secrets and raising questions about how it differs from similar phenomena on Earth. The discovery of the Martian night glow came as a surprise to researchers. Unlike Earth's air glow, which is caused by the interaction of sunlight with molecules in our atmosphere, the glow on Mars appears to have a different origin. On Earth, airglow is a result of oxygen and nitrogen molecules releasing energy absorbed from the sun during the day, creating a soft, colorful light in the night sky. But Mars, with its thin atmosphere composed mostly of carbon dioxide, presents a unique set of conditions that make its night glow distinct. So, what causes this mysterious glow on Mars? Scientists believe it is linked to the breakdown of carbon dioxide molecules in the planet's upper atmosphere. During the day, ultraviolet light from the sun splits carbon dioxide into carbon monoxide and oxygen atoms. At night, these oxygen atoms recombine, releasing energy in the form of light. This process creates a faint greenish glow that is visible from orbit and, in some cases, even from the surface. The glow is not constant. It varies in intensity and location, adding another layer of intrigue to this phenomenon. What makes the Martian night glow particularly fascinating is how it differs from Earth's airglow. On our planet, airglow is relatively uniform and predictable, but on Mars, the glow is patchy and dynamic. This variability suggests that Mars' atmosphere behaves in ways we are still struggling to understand. For instance, the glow appears to be influenced by the planet's seasons, with stronger emissions occurring during certain times of the year. This seasonal pattern hints at complex interactions between the atmosphere, solar radiation, and even the planet's magnetic field or lack thereof. The significance of the Martian night glow extends beyond its beauty. By studying this phenomenon, scientists can gain valuable insights into the composition and behavior of Mars' atmosphere. For example, the glow provides clues about the distribution of oxygen atoms and the processes that drive atmospheric chemistry. It also helps researchers understand how energy is transferred and dissipated in the thin Martian air, which is crucial for modeling the planet's climate and weather patterns. Moreover, the night glow has implications for future exploration. Understanding how Mars' atmosphere behaves at night could inform the design of spacecraft and instruments, ensuring they can operate effectively in the planet's unique environment. It could also help us better predict atmospheric conditions for future human missions, making it easier to plan safe landings and surface operations. As we continue to unravel the mysteries of the Martian night glow, each observation brings us closer to understanding the red planet's atmospheric dynamics. This faint glow is more than just a celestial curiosity. It is a beacon guiding us toward a deeper understanding of Mars' past, present, and future. Next, we'll explore another intriguing aspect of Mars' surface, the discovery of perchlorates in its soil and the challenges they pose for potential life and human exploration. Now, let's turn our attention to the Martian soil, where another puzzling discovery awaits perchlorates. These chemical compounds, found in abundance on Mars, have sparked both excitement and concern among scientists. Perchlorates are salts containing chlorine and oxygen, and while they might sound like a minor detail, their presence on Mars has profound implications for the search for life and the future of human exploration. The discovery of perchlorates in Martian soil came as a surprise during the Phoenix lander mission in 2008. Since then, other missions, including the Curiosity rover, have confirmed their widespread presence. On Earth, perchlorates are relatively rare and are often associated with arid environments like deserts. But on Mars, they seem to be everywhere, raising the question, how did they become so abundant? One theory suggests that perchlorates form through the interaction of ultraviolet light from the sun with chlorine compounds in the Martian soil. Over billions of years, this process could have led to the accumulation of these salts. Another possibility is that perchlorates were deposited by ancient volcanic activity or even delivered by meteorites. Whatever their origin, their abundance on Mars is a mystery that continues to intrigue researchers. The presence of perchlorates has significant implications for the search for microbial life on Mars. On one hand, perchlorates can be a source of energy for certain types of microbes. Some Earth-based microorganisms are known to metabolize perchlorates, using them as a food source. This raises the tantalizing possibility that similar life forms could exist on Mars, thriving in the planet's harsh environment. On the other hand, perchlorates are highly toxic to most forms of life, including humans. Their presence in the soil could make it difficult for any potential Martian microbes to survive, let alone for future astronauts to explore the surface safely. This duality makes perchlorates both a potential biosignature and a hazard. For scientists, the challenge lies in determining whether these compounds are evidence of past or present life, or simply a chemical quirk of the Martian environment. For engineers and mission planners, the challenge is even greater. Perchlorates can break down into reactive chemicals when exposed to heat or radiation, posing risks to equipment and human health. Future missions will need to account for these dangers, whether by developing protective technologies or finding ways to neutralize the compounds. The mystery of Martian perchlorates also ties into broader questions about the planet's history. Their abundance suggests that Mars' environment has been chemically active for billions of years, shaped by processes we are only beginning to understand. By studying these salts, scientists hope to piece together the story of how Mars evolved from a potentially habitable world to the barren landscape we see today. As we continue to explore the red planet, perchlorates will remain a key focus of research. They are a reminder of the complexities of Mars, a world that challenges our assumptions and pushes the boundaries of our knowledge. Next, we'll delve into one of the most tantalizing mysteries of all, the potential existence of underground lakes near Mars' south pole and what they could mean for the search for life. Shifting our gaze to the icy depths of Mars' south pole, we encounter one of the most tantalizing mysteries, yet the potential existence of underground lakes. In 2018, scientists made a groundbreaking discovery using radar data from the European Space Agency's Mars Express orbiter. Beneath layers of ice, they detected what appeared to be a large body of liquid water stretching nearly 12 miles across. This finding sent shockwaves through the scientific community, as liquid water is a key ingredient for life as we know it. The idea of liquid water on Mars isn't new, but the discovery of these subsurface lakes challenges our understanding of the planet's environment. Mars' surface is far too cold for liquid water to exist, with temperatures often plummeting to -80 degrees Celsius. So, how could these lakes remain unfrozen? One leading theory suggests that the water is kept in a liquid state due to the presence of salts, which lower its freezing point. Perchlorates, the same compounds we discussed earlier, could play a crucial role here. Dissolved in water, they could create a briny solution that resists freezing even in the frigid Martian conditions. But the mystery doesn't end there. Maintaining liquid water beneath the ice would require a significant heat source, and scientists are still debating what that could be. Some propose that geothermal activity, such as heat from the planet's interior, might be warming the subsurface. Others suggest that the thick ice layers above could act as an insulating blanket, trapping heat and preventing the water from freezing. Whatever the explanation, the existence of these lakes raises profound questions about Mars' past and present habitability. The implications for life are immense. If liquid water exists beneath the ice, it could provide a stable environment for microbial life to thrive, shielded from the harsh radiation and extreme temperatures on the surface. On Earth, similar subglacial lakes like Antarctica's Lake Vostok are known to host unique ecosystems. Could Mars' underground lakes be hiding similar secrets? The possibility has fueled excitement and speculation, but confirming the presence of life, or even liquid water, remains a daunting challenge. Future missions will need to explore these regions more directly, perhaps using advanced drilling technology or specialized instruments to analyze the water's composition. The discovery of these lakes has already reshaped our understanding of Mars, transforming it from a dry, barren world to one that might still harbor pockets of liquid water and potentially life. As we continue to unravel the mysteries of the red planet, these hidden lakes stand as a beacon of possibility, reminding us that Mars still has secrets waiting to be uncovered. And with that, we've reached the end of our journey through 30 of the most baffling phenomena on Mars. From the face on Mars to these enigmatic underground lakes, each discovery has deepened our fascination with the red planet and challenged our understanding of the universe. Which of these mysteries intrigues you the most? Let us know in the comments below, and don't forget to like, subscribe, and hit the notification bell for more deep dives into the wonders of space. Until next time, keep exploring. As we wrap up our exploration of Mars' most baffling mysteries, it's clear that the red planet is far more than a barren, dusty world. From the enigmatic face on Mars to the seasonal dark streaks of recurring slope lineae, and from the puzzling methane spikes to the potential underground lakes near the South Pole, each phenomenon challenges our understanding and sparks our curiosity. These 30 unexplained mysteries remind us that Mars is a planet of endless intrigue, holding secrets that could reshape our knowledge of the universe and our place within it. Scientists around the globe are tirelessly working to unravel these mysteries, using cutting-edge technology and innovative missions to probe deeper into Mars' past and present. Every discovery, whether it's the spider-like formations in the polar regions or the ancient riverbeds that hint at a watery past, brings us closer to answering the ultimate question: could Mars have ever supported life? And if so, what might that mean for us? But the journey doesn't end here. Each mystery we've explored today is a piece of a larger puzzle, and solving it will require not just the efforts of scientists, but also the curiosity and imagination of people like you. What do you think lies beneath the Martian surface? Could there be microbial life hiding in those underground lakes, or are the methane spikes a sign of something even more extraordinary? Share your thoughts and theories in the comments below. We'd love to hear your ideas. If you've enjoyed this deep dive into the mysteries of Mars, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss out on the latest space discoveries. The universe is full of wonders waiting to be uncovered, and we're just getting started. Until next time, keep looking up and keep exploring.